So we want to use this inverse. The inverse in the, let's say, in the world of linear relations is very simple. Yeah? It is just, here's the definition. Yeah? This is my subspace, and the inverse is just switching the entries. That's all, done. Yeah? Of course, you get other problems, clearly. Yeah? It's not so simple, the inverse, like where is it defined? It could be what we say multi-valued, so here could be a 0, right? And then you have elements like 0x and stuff like this. This will be topic of today's talk, how to handle this. Yeah? Okay, and why are matrix pencils interesting? I mean, matrix pencils are interesting a lot in its own already, yeah. But the standard I just want to mention is the standard application is, of course, differential, so-called differential algebraic equations. Yeah, if you take this kind of Cauchy problem, yeah, generalization of the Cauchy problem, where here is some matrix. You can also put their operators in infinite dimensional spaces, but not today. Where here's some matrix, let's say not invertible, then you do the same as in the Cauchy problem. You look at this matrix equation, or you investigate this pencil. Huh? I recall it a little bit just to get an idea what are we going to do, and I mean in the application, what is one going to do? Okay, yeah, I compare it with the Cauchy problem here, and here's our. Actually, it is not differential algebraic equation. It is. Sorry. And then, as I said, we associate and the Cauchy problem this guy. Here we associate the matrix pencil, or what we are going to do. This becomes now looks like an eigenvalue problem for linear relations, right? If we do this identification, as I said, I will discuss it more in detail. And then we have, everybody knows, Jordan normal form, Jordan canonical form, which is given by Jordan chains, by eigenvectors and associated vectors. And when you have this is very sloppy, you get the solution of your differential equation. I didn't put it here. You know it, everybody has to know it, yeah, like exponential and eigenvectors, and so on and so on. No? The standard formula for the solution of the Cauchy problem when A is a matrix. No? And the solution is built out of eigenvectors and the associated vectors, and surprisingly enough, there is nothing like Jordan form. There's nothing like this for subspaces, which is a little bit surprising, I have to say. Okay, and I don't go to the solution theory. There's a super big solution theory for differential algebraic equations, but this is not my topic. No? Okay, so. I mean, this relation between these two is rather simple, one has to say, between the matrix pencil and this linear relation. But it makes no sense to translate matrix pencils into linear relations if you don't have anything to offer, let's say. Yeah, you need something what you are going to do in then with a so that was, let's say, our motivation to understand what are these let's say Jordan form. Huh? So the idea of today's talk is a little bit I show you how this guy looks like, and then I discuss the relation between the pencil and the subspace. Huh? Okay. So yeah, now we have to do a little bit of, let's say, notions. Yeah. So it is 2 slides. I could make it into 2 slides. So it's a little bit boring, sorry, but I have to introduce the notions. First of all, of course, subspaces are not matrices. Huh? But if you, it's the standard, the best example, well, the best well-known example for us is, of course, subspaces generated by a matrix. And the standard subspace I have in mind is, of course, the graph of A. This is a prime, the prime example of a linear relation. So this, of course, it looks like this. XAX, a collection of all XAX is the graph of A, and this is obviously a linear relation. It's a subspace of this Cartesian product, done. And very often, sloppy, we just identify. So if we write a matrix, the matrix is always, in our understanding, not always, but almost always, a linear relation given by its graph. But we don't want to write graph. So very often, a little bit sloppy, we identify the matrix A with its graph, just to make things easier. And from the, okay. Then we look at the, well, clearly, eigenvector and eigenvalue looks like this, right? So it looks like x lambda x. So, and this guy is obviously in the graph of A. Well, how I will define eigenvector and eigenvalue of an arbitrary linear relation? Well, like this, right? I don't need matrix properties for this. No? So it is just, So we take an arbitrary linear relation, and then eigenvector and eigenvalue, of course, are defined in this way. And in this, oh, now I did something bad. There's one. I jumped out of the, thank you. And in this style, of course, and I don't go into details, we now can transfer many notions from the matrix world into linear relations, like kernel, range, domain, obvious. No? So, and this I don't go into detail. I just push. It's some domain, all first entries. No? Kernel goes to 0. Range, all second entries. Spectrum or point spectrum. So kernel is not the 0 vector. What else? This is some special thing with linear relations. We always add infinity, or we consider infinity also to be an eigenvalue. Well, as I said, we can, this we already discussed, we always can invert. Well, I wrote it like this. Infinity is an eigenvalue if we have this, but you see, this is nothing else to say that 0 is an eigenvalue of the inverse. And in this sense, this way, it makes sense to attach infinity as an eigenvalue. Makes also things easier because you can, okay. This is something which, of course, is not coming from the matrix world. This is a so-called multi-valued part, where 0 is mapped to something non-zero. This is, of course, different from cannot happen with matrices, clearly. And then the product is the same like the product of two matrices. We have the only thing you have to do, right? You see here x and y, and there's something in between. So this is z is if they are matrices, then z is obviously bx, and then you have bx goes down here. This is abx. abx. So it is if A and B are matrices, it is the same. Well, and if there are subspaces, you do it like this. Let us just to exercise a little bit. Yeah? Let us make a small exercise. Of course, I will need it later, but to get the notions a little bit, this is my exercise. I said already that this kind of this guy is interesting for me because we will relate it to matrix pencil. Huh? Matrix pencil with coefficients which of the form lambda e minus a. And again, also important, always in this notion, for example, A and E are matrices. And of course, we don't want to write here E minus 1, no, or graph E minus 1, graph A. No, huh? It doesn't help. You have to learn, in some sense, how to read it in the right way. Huh? So this is what I want to recall here, the identification between A and its graph. Otherwise, again, yeah, notation will kill us. So, in fact, this guy is a matrix, and the linear relation via its graph. This E is a matrix, but E minus 1, of course, not in general. Huh? Okay, let us start. So here we use the formula from before. Maybe I go quickly back. Yeah. So we have x, y here, and a z. We need a z in between, let's say. Yeah? Sloppy speaking. Okay, here's the same, yeah? X, y, z in between. And the first one is from this guy, and the second one is from this. Just first line is just definition of a product. Yeah? And now, of course, we use now. First of all, we use the definition of the inverse. It's just switching the elements. Okay, fine. And next line, now we use, of course, the property that A and E are not general linear relations, they are matrices. So, which means that this guy is in the graph of A, again, identification. This guy is in the graph of A, this one is in the graph of E. What does it mean? If this gun is in the graph of A, the Z equals AX. No other choice for matrices. And the same with E. But we have, from this line to this line, we have one more property. Second entries are the same, which gives this. Yeah? This information is useless, right? Because this is always, if I start with X, then AX is in the graph of A, so nothing new. So we can drop this information, and here, and this is the kernel of this. Yeah? So this guy is the kernel. You see, this becomes higher dimension. Yeah? Because this, you have to read, it's not A, it is a long matrix. First part of the matrix is A, and the second part is minus E. No? Here, I mean, you see it here. Okay, that's all. So far, this is all. And now we make something easy. I want to spend 5 minutes on Jordan canonical form. Of course, I know everyone is totally aware what is Jordan canonical form. It is just, I don't know whether it is interesting. I like it. I want to write it in a specific way. No? The idea is a little bit, this is the next step. What is the difference between subspaces and matrices? I mean, it's clear they are different, but to understand what is really the difference. I mean, what is so for this, I want to rewrite Jordan form or a canonical form in a linear relation style. Yeah? In a style where we don't use A anymore. Yeah? Okay, it is easy. Yeah. So I recall standard facts. What do you need for Jordan canonical form? You need Jordan chains or eigenvectors and associated vectors. And this is the definition, right? So this is our here. This is our eigenvector. This is our eigenvalue, and so you have maybe a chain. No? So this would correspond to a Jordan block in your canonical form of size, I think size n times n, let's say. Yeah. Okay. Now as I said, I have to remove A in some sense. Huh? Okay. How to do it? Well, just use these equations. Huh? Just solve it. And now we identify, and what does it look like? Look. Yeah? These elements are in the graph of A, or I just wrote here A. Yeah? So this is obviously I don't do it, but in the next step you would say, okay, yeah, this is a Jordan chain for elements like this are a Jordan chain for linear relations. But I will not go to it in this talk. Yeah? So I don't do it here. Okay, this is obviously a Jordan chain at lambda for A, or it would be also a Jordan chain at lambda for a linear relation A, if you want. No? And then comes, of course, Jordan canonical form. Maybe, sorry, like this. No? This now is what you take one eigenvalue and collect all chains. You fix one eigenvalue, collect all chains. They look like this, and you get really trouble with the numbering, let's say, yeah. But okay, yeah. And because this is important for later, you see these guys. So the notion is, you see, it's not only one chain. There could be, of course, 80 chains of this form, yeah? And 100 of this form, and 250 of this form. Yeah? So you get some numbers here to describe this. How many chains are of length 1, how many are of length 2, and so on and so on. Yeah? And these are these numbers, and they have a name, and they are wire numbers. Yeah? These are wire numbers which describe how many chains of a specific length you have. And one way to write it down is like this. Yeah? There exist also Segren numbers, which are more well known. This is counting the block sizes. They are conjugate to each other, stuff like this. Yeah? And yeah, so they get the name W. And of course, you can have more than one eigenvalue. You have several eigenvalues, and so on and so on. Yeah? And then the one interesting fact, which nobody in linear algebra would ever make a point out of it, is that we have only chains of this type. All possible chains in the graph of A looks like this. Or to be more precise, I could also make some stupid things and add chains together. But if I always find a basis in this style. This is Jordan canonical form, and then they look like this. Yeah? Good. This is one thing, and the other thing is, which you all know, two matrices are similar to each other if and only if the wire numbers coincide, or what is the same, they have the same block structure, the same Jordan canonical form. Huh? So this is the main reason. We don't go too much into this. This is standard stuff. No? The wire number. I wanted to have the wire numbers, no? Because this I will use later. Okay, so that's it. Precisely. No, it's not so important. I can say it. Now I want to study what can happen with linear relations. No? What goes wrong? And there are 3 different cases. And well, they have also some kind of names, but I don't want to say something. Well, this is clear. We already had it, right? It can happen that we have 0x elements. And of course, in the Jordan normal form, they won't appear. Yeah? It's not possible. It's only for linear relations which are not matrices. Also, we could have more than one, could we have such a chain structure. Okay. Second so-called singular part, they are really very mean. They start at 0 and return to 0. So you see, they start at 0 and go somewhere. They start at 0 and go to 0. No? If you have something like this, then you see you can add this element. You multiply this element by lambda. We are in the subspace, right? Linear relations are subspaces. So I can add elements and I can multiply this. I multiply with lambda and add these 2 guys. Then I get this one. But this one is a Jordan chain. It is in the kernel of A3 minus lambda. This one is in A3 minus lambda. Huh? So, yeah, I wrote it there. Yeah, this one is in A3 minus lambda. And we get, because lambda was arbitrary, and you see that with infinity is this, no, with infinity you get for free because you have 0x, right? This is the eigenvalue. Everywhere in the plane eigenvalues. It's a little bit surprising. Okay. And the same we could also, I just want to show you a little bit chains. You could also place some in between, and it's the same. You get also the point spectrum of A4 is the complex plane. And the third guy is called multishift. And as I said, I just want to indicate that they are studied and have names and so on. Now we looked at something like this, and you see it is, well, this very small guy, let's say it's a one-dimensional linear relation, right? Consists only of one element. And of course, you cannot, no matter how you multiply and add, you will never get a 0 in the second component because these 2 guys are linear independent. So this means we have no point spectrum at all. This indicates a little bit that spectral theory for linear relations is maybe not so simple, let's say. And we are, I mean, what I sometimes find very fascinating, we are still in finite dimensions. It's normally in functional analysis, you think, yeah, finite dimensions. Okay, and also we could make the chain longer, which is not so important. And now comes the first main result, and this I want to discuss a little bit. Now, this is very new. We recently, it's only submitted. It's not accepted. This is now some sort of Jordan decomposition for linear relations, and it consists of essentially of four ingredients. No? Yeah, this one I will discuss them. Yeah, this one is looks like this is a Jordan. These are Jordan blocks, classical Jordan blocks, corresponding to a specific eigenvalues. Yeah. So in this sense, our decomposition into this, and this stands for direct sum. This is direct sum. Is a generalization of Jordan canonical form. Yeah? And what you get Jordan canonical form plus 3 more: async, J infinity, AM. Singular corresponds to singular chains, corresponds to chains at infinity, and corresponds to multi-valued chains. Yeah? So there was a reason why I showed you this example. Yeah? At infinity, singular, multi-shift. Yeah? Okay. Yeah. So I still have something like 15 minutes, right? And some, of course, not every linear relation has, of course, all entries. Yeah? So some might be 0. Here is the explanation. Here is the explanation for what means reduced. But maybe I skip it. It's technical. It is super important to make it unique, but it's technical, and I think I can explain it, but it will not really help, I think, at the moment. If you want to be in a discussion, of course, we can come back to the point. Yeah. So this this one is explained here. I said it already. Lambda J consists of Jordan blocks. This corresponds to infinity. If I take its inverse, then it's again Jordan blocks at 0. Huh? So these, so let me start. I decided for this talk, in order to make things easy, I don't define it correctly, let's say. Yeah? I just show you how they look like. Huh? Then you get some expression. Because if I try to do it exact, pages. Huh? So again, these guys are, yeah, I go back because they look like, each of them looks like this. Yeah? So for each eigenvalue, lambda 1 to lambda L, I have such a structure. Of course, then the indices also depend on the eigenvalue and so on and so on, yeah? As usual. So this is easy. So now we go to now we go to this guy. How does it look like? Well, I just show you the structure. Yeah? And yeah, it is J infinity. It is the chains at infinity. The chains at infinity are connected with the multi-valued part. And that's why they start all with 0 and have some length. Yeah? And again, I can write down, yeah? I start with the longest, second longest, blah, 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 and count. Yeah? And these numbers are here. I forgot to make it blue, sorry. And count them. And then, of course, these are my next wire numbers. Yeah? Because now I counted everything for the Jordan part, let's say, for the Jordan normal form of my linear relation. And now I start to count the other entries. And well, these are the numbers at infinity. Yeah? Well, it used here some. So wire numbers at infinity. And the rest is similar. Yeah? So now we go to a thing. Let me go quickly back. A thing is here. Next we make a thing, and then comes AM, and we are done. And it is always the same. Yeah? A thing looks like this. So what was a thing? Singular chains. They was the guys who started at 0 and go to 0. Huh? Same game. Yeah, I count the chains, and this gives me B. Yeah? And you can imagine the next is multi-valued part. What was this? Yeah, yeah. Everything linear independent. I don't say this all the time. Yeah? When I write it down, it's always linear independent. These was the guys with 2 linear independent entries. And I mean, in some sense, yes. Of course, we can state it in a different form. Yeah. Of course, all these things can happen in an arbitrary linear relation, clearly. So the interesting thing is, let's say, the other direction. This is all what can happen. No? So every linear relation admits a unique, I don't state it here, they haven't stated it here because it's connected with the reduced sum decomposition into this. And now comes, we collect all the numbers. Of course, these, you see I'm sloppy with the J and so on. Huh? It's a little bit sloppy notation, everything. You don't know what J runs from where to where and so on. Yeah? But I think it's clear. Yeah? So we collect all the wire numbers of our, let's say, regular or Jordan part. These are these numbers. Then comes infinity, singular chains, and multi-shift. And of course, we put them all together and call it the wire number related to our linear relation, or connected with our linear relation. And well, this is, it's first nothing special, but now, of course, it comes two subspaces with the same wire numbers are strictly equivalent. What is strictly equivalent? It's here. Yeah? Two linear relations with the same wire numbers are strictly equivalent and vice versa. Huh? And what is strictly equivalent? This one. Like what you would expect. Be a little bit careful. T is a matrix. This is but this is a linear relation. So this product means product between linear relations. Otherwise, it's not possible. So we have again to think of not of T, of graph of T. Huh? And then but it's really, it's really funny that it looks like the standard similarity property of matrices. Yeah? Well. Good. So this is what I wanted to show. Now I come slowly to an end, but I have to go back to matrix pencils before. And yeah. Oh, sorry, this is too quick. So as I said, I want to relate the matrix pencil lambda e minus a with the kernel of this linear relation. Sorry, no, this was wrong. Not with the kernel, with this linear relation. Sorry. Huh? And there's a mistake, of course. Yeah, sorry. Then we have, if we look at this matrix pencil, and this we will use as the definition for eigenvectors of matrix pencils. In this sense, in this case, we will say X is an eigenvector and lambda is an eigenvalue of the matrix pencil. So if this eigenvalue equation is satisfied, then here yeah, X is in the kernel of E minus 1A minus lambda. I forgot this. I was too nervous. So lambda E minus A X is 0 if and only if X is in the kernel of E minus 1A E minus 1A minus lambda. Huh? I mean, this is what you expect, let's say. Yeah, you sloppy speaking, you multiply with E minus 1, and then you get it. Yeah? Let's say if E is an invertible matrix, this would be clear. Okay, but now we can write it also in this way. And okay, this is, if you want to check it, this is just one line. It's nothing, actually nothing special. Did I something? Ah, yeah. So what I want to do is, I want to relate chains or Jordan chains of the. You remember the definition, yeah? Jordan chains for linear relations we have. I write it in a different way here. I wanted to relate to the Jordan chains of a pencil. And for this, I have to introduce Jordan chains of a pencil. Huh? And this is done. This is done here. Huh? Yeah, please. Yeah, this is wrong. Oh, please forget this. So how we are doing it? Okay, it is it is like above. It is an eigenvector and eigenvalue. Yeah? And then we go up like this, and here is some speciality in for pencils. You have to write the E there for some reason. Yeah? But this is standard. It is how you have to do it. Otherwise, you get the wrong chains. Let's say. Yeah? Okay, this is the definition for matrix pencils, and then we collect them all. So now we have Jordan. We have. I will not use it, but nevertheless, we have, if you want, we have some sort of Jordan chains for the pencil, and now we have Jordan chains. We have Jordan chains for the pencil. We have also Jordan chains for the linear relation, and we want to relate them to each other. And here is, this is now the collection of all Jordan chains of a specific length. Yeah? So this is what we want to investigate. And I just want to show you one. This is all what I want to show you. Now, again, these are the number. This number here is what? This is the number of Jordan chains. It's also written down here. Yeah? This difference of these two guys, yeah, is the number of Jordan, because I subtract this dimension here, is all the guys which are k, which have length k or more. Yeah? This is this number of the pencil. Now we want to relate it to a linear relation. Of course, we take as a linear relation this one here, E-1a, which have all the time. Yeah? And I think I found this result nice. It is this. The corresponding wire numbers. Yeah? So this is eigenvalue. We investigate eigenvalue lambda. Yeah? And this guy was the regular part of my canonical decomposition, the Jordan blocks. And this Bj was for the so-called singular part. This Bj comes from the singular part, and we have this identity. Why this one? In fact, we have complete control over the numbers of the pencil and of the pencil and of this guy. But to explain this is very extensive, huh? More than one talk, let's say. So this one is easy to explain. Yeah, because you can do it. You have the corresponding definitions very quickly. Okay, so let me give some overview, outlook or summary also. First of all, what we discussed, each linear relation allows decomposition into 4 different parts, which are singular part, Jordan part, infinity, and multi-shift. Yeah? This is what I mean with 4. I mean, it was much more, but yeah? So okay. And there is another object, but I don't go into detail because I think most of you will not know Kronecker canonical form. And this is the canonical form for for matrix pencils, which is well established. Yeah, it is here. So this Kronecker canonical form comes from Kronecker and is 150 years old, about 1882, something like this. I don't write it down because this takes some time. And it has also 4 entries. 4 entries, and the statement is what? There exist 2 invertible matrices, S and T, and if you multiply it with a pencil, you get a normal form with 4 different kinds of blocks. One looks like, because E, yeah, right? If E is identity, you have the standard matrix problem. So one part is Jordan type, one part is connected with infinity, with the eigenvalue infinity, and then there are two more with strange names, which doesn't help you. Also, it doesn't help me. And this is how it comes. So now you can guess what is also, of course, in this canonical form, you get wire numbers or Segre numbers, but I need wire numbers by counting the chain sizes or block sizes. Yeah? So this gives the so-called Kronecker indices. Of course, you also have 4 different types of indices, and which I didn't present today. They correspond to the wire numbers. The wire numbers of the Kronecker form correspond to the wire numbers of this guy, but with some small changes. And this is very nasty to explain. That's why I make it so general. Huh? So there's a lot of technical details, because there are some. It's clear why these shifts are there. They have a very good explanation. But nevertheless, it is a little bit tedious. Okay, and because we can go in both directions. This is the final sentence. Why it is interesting from my point of view, if you have some problem for matrix pencils, yeah, you go to linear relations and do something with linear relations, like perturbation theory, as I said, spectral theory, whatsoever. No? The standard stuff we are always doing with operators. No? For example, just to give you an example, what happens if you change the entries a little bit in E and A? If you want to, let's say you make a one-dimensional perturbation. Yeah, you know that Kronecker form will not help you. Jordan canonical form will not help you if you make one-dimensional perturbations. You have to deal differently, because the perturbed operator has a totally different Jordan form. Of course, it's well understood what happens, but just to explain. So then you go to this object. It is under the right assumptions. It is a one-dimensional perturbation of linear relations, and then you do relation things. Yeah, and then you can go back. It doesn't mean that it's like the classical things in mathematics, right? You have one problem, but 2 descriptions, 2 totally different descriptions, and this is often very helpful, because one description is very good for one problem, and the second one is much better for different class of problems. Yeah? And this is somehow the idea behind why it is interesting to have this relation between pencils and subspaces. Okay, thank you.